Welcome back. In the last video, I left you on the cliffhanger of implementing the forward method. So I hope you took on the challenge and gave it a shot of putting together all of the pieces of the puzzle to replicate or bring to life our own vision transformer, or VIT for short, of course. So let's start with the forward method. We've got everything we need. What do we need to do? So let's think about what the input is going to be. We discussed this right back at the start. The input is some sort of image. And then what do we need to do? Well, we need to move it through this embedded patches layer, the MSA block, the NLP block. But luckily for us, a lot of this is taken care of by the fact that we've put it all together in a transformer encoder. So let's see how we could do that. First thing we need to do is get the batch size. And this will make sense in a second. So batch size equals x.shape. We need the 0th index. Now, of course, we could hard code the batch size somewhere, but again, we don't like to hard code these things when we can manipulate our data so much. So regardless of whether we're using a batch size of 32 or like the paper, we're using a batch size of 4096, which we're not doing because, is it 496? Yeah, 4096, which we're not doing because we're a little bit limited with the hardware. So if you had bigger hardware, you could use a bigger batch size, but this will work regardless of the batch size. So now let's create the class token embedding and expand it to match the batch size. Now this is equation 1. You'll see what I mean by expanding it to match the batch size. So class token equals self.class embedding, which is of course created up here. This is why we need expand, the batch size. We want to expand the class token across all of the batches. And I'm going to put -1 here, and we'll see what this does in a second. So I'll just write down what it does and then we'll see it. Means to infer the dimensions. So just to show you, if we replicate what we're doing here, we'll get our class token. So here, I'm just going to write this. Embedding dim, and I'm going to set batch size. So embedding dim equals 768. And for a batch size of 32, which is what we're going to be using, let's have a look at what the class embedding looks like. We might actually change this to be ones. Actually, there's too many random numbers going on, so let's just look at the shape. Wonderful, so we've got that shape. Now, if we expand it, which is exactly what we're doing here, let's write this down. Class embedding, expanded. I hope you realize what we're doing. We're taking the pieces of the puzzle, and if we don't understand something, if in doubt, code it out. Let's expand the class embedding. .expand, and we want to expand it to batch size, which will be 32, and then we want to go -1, -1. So as you'll see, -1 means to infer the dimensions. So let's print that out. Print class embedding shape, print class embedding expanded. There we go. Oh, we need the shape. Easier to compare apples to apples. There we go. Wonderful. So we've expanded that class token embedding across every image in a batch. So that's what this line does, because we want to append in equation 1, or prepend, sorry. I always get those two mixed up. If we go right back to equation 1, we don't only want to create this. Well, so far we've been working with one image to demonstrate, but we're going to be passing batches of images to our VIT model. So we want to create an X patch embedding or image patch embedding for each image in the batch, and a class token as well for each image in a batch. So that's why we do that there. Now, if we jump back into here, we expand. Now what can we do? Well, let's create the patch embedding. So this is equation 1, and we go x equals self.patch embedding, and we'll pass in x as well, because x is just going to be here. So this is actually the first step of manipulation in our forward method. Then what do? Well, we want to concat class token embedding and patch embedding. So this is still equation 1. We're putting things together. This is so exciting. We're creating a VIT architecture, a vision transformer from scratch. So class token, and we want to concatenate it with X, which will be the output of our patch embedding. And we want to do it where? Across the first dimension. Why is that? Because this is going to be 32, number of patches, 768 embedding dimension. So we're doing it across batch size, number of patches, embedding dim. Beautiful. Now what do we want to do? Well, we want to add the position embedding to class token and patch embedding. So we can go x equals self.position embedding plus x, because that's going to be the output here. So if we go up here, there's our position embedding. We've created that on purpose to be a random initialization. And the size is self number of patches plus 1. Number of patches plus 1 will of course be number of patches plus 1, because we're concatenating the class token. Beautiful. And now what's next? Well, we can run embedding dropout from here. So if we look back up dropout, we've done this about half a dozen times now, but of course that's what the nature of paper replicating is, jumping all over the place. Dropout, when used, is applied after every dense layer, except for the KQV projections, and directly after adding positional to patch embedding. So this is what we're doing, directly after positional to patch embeddings. I'll just come here, apply dropout to patch embeddings, and I'll just make sure that's all on one line. Beautiful. So x equals self embedding dropout on x, and so embedding dropout is going to be this here with the probability of 0.1 by default, that is. We could change that if we wanted to. Now what's next? Well, we have to pass our position and patch embedding to the transformer encoder. So if we go back to figure 1, right up here to our colorful graphic we've seen so many times. We're getting so close, everyone. So we've embedded the patches, we've created this. That's what we've created. We've got a little dropout layer in here that isn't visible in this diagram, but that's the whole nature of paper replicating. You not only have to use images, math, you have to use text as well. We've got a transformer encoder layer. So let's pass our embedding, our patch and position embedding, through all of our stack of transformer encoders, which is created here. So we want to go x equals self.transformer encoder x. Wonderful. Now there's final step, the final step. So we want to put the 0th index, I'm not even sure if 0th is the right word, but I'm going to use it. 0th index logit through the classifier. And this is equation 4. And excuse me, this is going to be equation 2 and 3. 2 and 3. And so equation 4 is, if we go back, we've got this token here, the class token, that goes through the MLP head and outputs to something like this. So if we scroll down, this is y, so the output equals layer norm, our classifier, on the 0th index z, so logit, of the last layer. So we take this, the 0th index, and pass it through the self.classifier. So we want 0, we want every batch, and then we want the 0th index there. And I think that is a complete vision transformer architecture created. Look at that. Our first VIT. So that deserves a round of applause. So we haven't quite made sure that it works just yet, but we've put together a vision transformer from scratch, going through all of the pieces of the puzzle. What have we done? We've created equation 1, turned our image into a sequence of patch embeddings, created equation 2, a multi-head self-attention block, created equation 3, multi-layer perceptron, an MLP block, put them all together into a transformer encoder, and then put all of that together into a vision transformer class. So now we should be able to just call our vision transformer VIT equals VIT. Let's see if this works. Vit. Oh my gosh, look at that. Look at all those layers we just created. Now, my challenge to you to finish off this video, or to finish off this little section, is to run some data through the Vit instance that we have here and see what it outputs. Is it in the correct shape that we want? So do a little dance, pat yourself on the back, and finish the final test of putting some data through it. And perhaps you might want to get a summary of torchinfo.summary. Otherwise, we'll do that together in the next video. I'll see you there.